in the last lecture we were examining the heat conduction in a composite where the temperature field was a function of two coordinates in the spherical coordinate system. So, you have a sphere in a spherical coordinate system, and I want to examine the heat conduction from the sphere. I use a spherical coordinate system where one of the coordinates is the distance from the origin r, theta is the azimuthal angle, it is the angle made by the radius vector with the z axis, the plus z axis, and this angle theta varies from 0 to pi, 0 at the plus z axis and pi at the minus z axis. Okay. The third angle is the meridional angle phi, which is the angle made by the projection of the radius vector onto the xy plane with the plus x axis. Okay. So, these are the three coordinates in the spherical coordinate system. And this Laplace equation in a spherical coordinate system can be written as del square t is equal to 1 by r square d by dr of r square partial t by partial r. Okay, so, that is the Laplace equation in a spherical coordinate system. And when we solved the problem of heat temperature, heat conduction in a composite material, we had included only these two terms because the system was axisymmetric about the z axis, the axis, the direction of the average heat flux or the direction of the variation of temperature. Okay, so, because it was axisymmetric. Now, we will solve this for the general 3-dimensional case where the system is not necessarily axisymmetric. Okay. So, in order to solve this, the way it is done is separation of variables. Okay. I will not specify here the configuration or the boundary conditions, but I will restrict attention to what are the forms of the solutions that are obtained, okay, if you use separation of variables for this case. Recall that in a Cartesian coordinate system, when you use separation of variables, in the homogeneous directions you get sine and cosine functions. Okay. So, what we are examining here is what are the functions that we get in the homogeneous directions in this case. In a Cartesian coordinate system, you have boundaries in the x, y and z directions. If you had a rectangular or a cube or a cubical box, for example, you will have boundaries, and on those boundaries boundary conditions will be applied. In this particular case, the distance from the center is the r coordinate, goes from 0 to infinity in general, it has to be positive. The angle made by r with the z axis is theta. Theta goes from 0 to pi, okay, 0 less than or equal to r. Okay. And in the phi direction, okay, in typical configurations such as the spherical particle, for example, at the ends of the interval in the theta direction 0 and pi, there are no physical boundaries. Okay. There is no physical boundary at theta is equal to 0 or theta equals pi. Similarly, there is no physical boundary at phi equals 0 or at phi equals 2 pi, okay, unless you are sectioning the sphere somehow. Okay. So, there are no physical boundaries in the phi direction for a spherical particle. There are no physical boundaries in the theta direction for a spherical particle. So, the boundary conditions in both of these directions have to emerge from symmetries. When we solved the problem for the heat conduction in a sphere, right, in a linear temperature gradient. The solutions turned out to be Legendre polynomials, and the symmetry emerged from the fact that at theta equal to 0 or theta equal to pi, or we had defined this psi is equal to cos theta. Okay. So, -1 less than or equal to psi less than or equal to 1, okay, in terms of this modified coordinate psi. Okay. So, at the endpoints the solutions have to be finite. Okay. From that we got discrete eigenvalues in the psi direction. Okay. So, similarly in this particular general case, you will have to get eigenvalues in both the phi direction and the theta direction. Okay. Similar to how we got eigenvalues in the theta direction for an axisymmetric problem. Okay. And so, these are the homogeneous directions. The requirements that the solutions have to be finite, okay, or other symmetry requirements will specify what are the eigenvalues for the theta and phi directions. Okay. So, we define T is equal to f of r g of theta times h of phi. Okay. Substitute this into the conservation equation, divide throughout by f times g times h. Okay. Substitute into the conservation equation and then divide throughout by f times g times h. Okay. So, if you do that, right, so you will get 1 by f 1 by r square d by dr, or since I have done separation of variables, this will be total derivatives. Okay. So, substitute T as f times g times h, f is a function of r, g is a function of theta, h is a function of phi. Substitute into the Laplace equation for the temperature field, this del square T equal to 0. Divide throughout by f times g times h, and this is what you get. You can multiply throughout by r square sin theta. Okay. Multiply throughout by r square sin theta. Okay. And I will get sin theta, okay, into 1 by f, I am sorry, multiply throughout by r square sin square theta. Okay. Multiply throughout by r square sin square theta, okay, and I will get sin square theta, okay, into 1 by f 1 by r square d by dr of r square df by dr plus 1 by g sin theta okay. Okay, so, this is the equation that you get if you multiply throughout by r square sin square theta. My apologies, this 1 over r square should not be there because I multiplied by r square. Okay. Now, you can see that this first term here is only a function of r and theta, and this second term here is only a function of phi. Therefore, both have to be constants. Okay. And so, first things first, this implies that 1 over h d square h by d phi square is equal to some constant. Okay. And if that constant is positive, h is equal to a e power root c phi plus b e power minus root c phi, exponentially increasing and decreasing. Okay. On the other hand, if that constant is negative, is equal to minus m square, okay, then h is equal to a cos of m phi plus b sine of m phi. These are the two possibilities. Okay. So, which one is it? Is it positive or negative? Okay. For that, let us examine physically what this angle phi is. Okay. So, this is the z axis, this is y, this is x. Okay. This is any location, okay, in which r is this coordinate and this is theta, and phi is basically the angle around the z axis. Okay. Phi is the angle around the z axis. Okay. So, as you go around the z axis, this radius vector basically traces out a cone. Okay. It traces out a cone, okay, as you go around the z axis. My cone is not quite regular, so let me try to correct that. Okay. It traces out a cone, okay, as phi goes around the z axis. Okay. So, if I go once around the z axis, and that means that I increment phi by an angle 2 pi. Okay. If I go once around the z axis, I increment the angle phi by an angle 2 pi. And when I increment phi by an angle 2 pi, I come back to the same physical point in space. Okay. And therefore, at the same physical point in space, all properties have to be exactly the same. Okay. So, that means any property has to be the same if the angle phi is incremented by 2 pi. Okay. If phi were the sum of two exponentials and you increase phi by 2 pi, the value of that function h will not in general be the same. Okay. You cannot because as you go around by an angle of 2 pi, if you have to come back to the same physical point in space, you know that these exponentially increasing and decreasing functions either decrease exponentially or they increase exponentially. Okay, these exponentially increasing and decreasing functions of phi, okay, phi versus h, okay, these either increase or decrease exponentially, and if you increase phi by an angle 2 pi, they will not revert to their original values. Okay, they will not come back to their original values. So, this requirement that when you go around by an angle phi, you come back to the same physical point in space means that this constant cannot be positive. Okay, because exponential functions are not periodic, they do not come back to their original value when you increase by 2 pi. Sine and cos functions are periodic. Okay, sine and cos functions are periodic. They do come back to their original values when you go around by 2 pi, only if m is an integer. Okay, only if m is an integer. If m is equal to 1, 2, 3, etc. Therefore, if I increase angle by phi by 2 pi, that means that the argument of the sine and cos increases by 2 m pi, and if m is an integer, then the sine and cos functions are the same as what you would have at the original location where phi was equal to phi. If you increase phi by 2 pi, you come back to the same location. Therefore, this requirement that when you increase the angle phi by 2 pi, you have to come back to the same location in space, implies that this constant has to be negative and it has to be minus m square, where m is an integer. Okay, where m is an integer. Okay. And the solutions are in general, okay, the solutions of this are in general H is equal to sigma am cos of m phi okay. General solutions of this form will satisfy the periodicity condition in the phi direction. Okay. In this case m is equal to 0 to infinity. Okay. An alternate way of writing this is to write it as e power I m phi. Okay. Okay. The real part of this is the cos function, the imaginary part of this is the sine function. Therefore, by choosing a suitable complex coefficient a m, I can recover these two functions cos m phi and sin m phi. However, in this case m has to go from over both negative as well as positive values. Okay. M has to have both negative and positive values. Okay. So, therefore, we will use this notation here for h. Okay. A m, which is a complex function, times e power I m phi. Okay. This is h, and this solution is also orthogonal. Okay. So, if I take h m is equal to a m times e power I m phi. Okay. The orthogonality relation in the case of a complex function is defined as integral 0 to 2 pi okay, of d phi of h m of phi times h n star of phi. Okay. In the case of complex arguments, you have to take the one function h m times the complex conjugate of the second function h n in order to get a solution that is real, okay, because the orthogonality relation has to give you a real solution. Okay. So, this is equal to integral 0 to 2 pi d phi into e power I m phi into e power minus I n phi. Okay. To get the complex conjugate, you have to change the sign of the complex of I, okay, in the complex function. Okay. So, therefore, the complex conjugate of e power minus I n phi, okay, which will be equal to the complex conjugate of the complex conjugate of e power I n phi, okay, is equal to the complex conjugate of cos of n phi minus I plus I sin of n phi. Okay. Okay. The complex conjugate of e power I n phi, in the complex number you change the sign of the imaginary part. Okay. So, this is equal to cos of n phi minus I sin of n phi, okay, which is equal to e power minus I n phi. Okay. So, the complex conjugate of e power I n phi, that is h n of phi, is just equal to e power minus I n phi. Okay. So, if you have a complex number, you can just get its conjugate by changing the sign of the square root of minus 1, okay, or changing the sign of I in that complex number. Okay. And you can easily verify that this is equal to 2 pi for n is equal to m, okay, because for n is equal to m, the argument just becomes 1 and I have integral of d phi between 0 and 2 pi, that is just equal to 2 pi, and this is equal to 0 for n not equal to m. Okay. Because if n is not equal to m, then you have e power I times some integer times phi, because n minus m is an integer. Okay. E power I times some integer times phi between 0 and 2 pi is going to be equal to 0, because when you increment phi by 2 pi, you come to the same location in space Therefore, the value of the function at the initial and final locations are the same, and the integral turns out to be 0. Okay. So, therefore, you have this orthogonality relation. Okay. This is equal to 2 pi delta m n. Okay. So, therefore, the basis functions in the phi direction are e power I n phi, where n is an integer. These satisfy the orthogonality relation. The orthogonality relation in the case of a complex function, you have to multiply the first function and the complex conjugate of the second function and then integrate it, and this turns out to be 0 if n is equal to m, I am sorry, if n is not equal to m, and it is non-zero only if n is equal to m. Okay. So, this is equal to 2 pi times delta n m. Okay. So, that is the solution in the phi direction. Okay. Now, I have to solve the rest of this. Okay. I have to solve the rest of this, and here I have to substitute minus m square, okay, because we have d okay, because of this relation. Okay. So, I will get sin square theta into d by dr of r square df by dr and I can divide throughout by sin square theta, okay, where m is an integer. Okay. Okay, divide throughout by sin square theta. So, I will get a sin square theta here, okay, and remove this. Okay. And you can see that this second term is only a function of theta. Okay. This second term is only a function of theta. The first term is only a function of r. Therefore, both of them have to be equal to constants. What should that constant be? Okay. So, first let us take the constant in the theta direction, okay, 1 by g sin theta is equal to some constant alpha n. We had solved for that constant for the special case where m was equal to 0 in the axisymmetric problem, and we had got this constant as minus n into n plus 1. Okay. Okay. We had got that for the special case where m was equal to 0. In the general case, for a non-axisymmetric problem where m is in general not equal to 0, the solution is very similar. Okay. The solution is of the form g of sin theta is equal to what is called the associated Legendre polynomial of g of cos theta. Okay. If this term here is of the form n into n plus 1, okay, where n is an integer. Okay. So, first of all, n is an integer. Okay. Okay. I had worked it out in the case of an axisymmetric problem to get the Legendre polynomials earlier. Okay. Okay. and m varies between minus n and plus n. Okay. N is a positive integer. Okay. We had got that earlier as well. For the Legendre polynomial series to be finite, you require that n is an integer when m is equal to 0. Okay. For the general case where n is not equal to 0, n is an integer and m is an integer. Okay, we just got that from the solution in the phi direction, and minus m minus n less than or equal to m less than or equal to n. Okay. That is, n is a positive integer, okay, n greater than or equal to 0. Okay. So, for the solution to be finite at theta is equal to 0 and theta equals pi, for an axisymmetric solution, for an axisymmetric problem, I showed you that n has to be a positive integer. Okay. I showed you that n has to be a positive integer. For the general non-axisymmetric case, for the solution to be finite at theta is equal to 0 and theta equals pi, I will just state here without going through the proof, because it is a little complicated. I will not go through the proof, but I will just state here that n has to be an integer, n is greater than or equal to 0, and m has to be an integer, and it has to be between minus n and plus n. Okay. So, if n is equal to 0, m has to be equal to 0. If n is equal to 1, m can take values of minus 1, 0, plus 1. If n is equal to 2, m can take values of minus 2, minus 1, 0, plus 1, plus 2, and so on. Okay. So, those are the restrictions on the integer m for the phi direction, the integer n for the theta direction. Okay. Those are the restrictions on these two integers. For the solution to be to have the same value when phi is increased by 2 pi, okay, because it is the same physical point in space, and for the solution to be finite at theta equals 0 and theta equals pi. And if this is equal to minus n into n plus 1, then the solution for the r direction, okay, the solution for the r direction just is obtained by just solving this one. And this provides us the solution f is equal to a r power n plus b by r power n plus 1. Those are the growing and decaying harmonic solutions. Okay. So, finally, the solution for the temperature field has the form over integer n is equal to 0 to infinity. Okay. I told you that the integer m for the solution to be finite at theta is equal to 0 and theta equals pi, the integer m has to go from minus n to plus n, okay, of a n r power n plus b n by r power n plus 1 p n m of cos theta e power I m phi. Okay. So, this is the generalization of the solution that we had got earlier. Recall that earlier we had just got sigma n is equal to 0 to infinity of a n r power n plus b n by r power n plus 1, okay, p n of cos theta. Okay. So, the Legendre polynomials that I had calculated earlier are the solutions for m is equal to 0. Okay. The general non-axisymmetric case for m is not equal to 0 is this solution here for the temperature field. Okay. It contains one part which is e power I m phi, alternatively can be expressed as cos m phi plus I sin m phi or e power I m phi. This is only a function of the phi coordinate. M has to be an integer because as you increment phi by 2 pi, one has to come to the same physical point in space. The theta dependence is through p and m of cos theta. These are extensions of the Legendre polynomials I had calculated earlier for the axisymmetric case, and these also can be calculated by recurrence relations, which I will not go into in detail at present. These are also orthogonal functions. Okay. And the orthogonality relation for p and m of cos theta is that integral sin theta n m of cos theta p n prime m of cos theta. Okay. If you multiply p n m of cos theta and p n prime m of cos theta and integrate over theta from 0 to pi, you will get it non-zero only when n is equal to n is equal to n prime, my apologies. Okay. I have used n and n prime here by n plus m. Okay. Factorial by n minus m factorial. Okay. Recall that for m is equal to 0, I just had 2 by 2n plus 1 because m was equal to 0. When m is non-zero, then this is the normalization condition for the Legendre polynomials, and the normalization condition in the phi direction was that 0 to pi d phi h m of phi h m prime star of phi, okay, is equal to 2 pi delta m m prime. Okay. M prime star, this is e power I m phi, and the complex conjugate of e power I m prime phi, which is e power minus I m prime phi. Okay. Okay, so h of phi is e power I m phi. Complex conjugate of h of m prime phi is e power minus I m prime phi. This also has an orthogonality relation. Okay, in the phi direction, it is 2 pi if m is equal to m prime, and it is 0 if m is not equal to m prime. So, this is the general solution for a non-axisymmetric case. We will examine this in a little more detail in the next lecture in terms of what are called spherical harmonic expansions, and then we will proceed to an alternative interpretation of these same solutions of the Laplace equation in a spherical coordinate system. So, I will continue this in the next lecture. I will see you then.